Only 13 participants are here. So let's wait a couple of more minutes, then we'll start the session. So today's session is a Solvitas session.
This is week 11.
Week 11 Solvitas. And it's already on portal. It's already available. I will show you all this. This is the last time I have shown you also. But let's discuss today also. And now I think today will be the last day, I think so, for the week 11, right? What is the deadline for week 11? I think it is graded assignment today.
30, sir, 30.
30. Oh, it is deadline is extended. Okay. Okay. So let me present my screen, then we'll start the session. I have a Solvitas slide. We'll do next to that. Okay, where is that? My screen is visible to all of you, right?
Yes, sir.
Okay. Just a minute. So as we know, week 11 have some algorithms like the extra algorithm and Bellman-Ford, Floyd, Vercel, Prescal. These algorithms we have, and also we have to find the. My voice is clear and is visible to all of you. Is that right?
Yes.
Okay. So the Dijkstra algorithm and Bellman-Ford, Floyd, these three are for only shortest to find the shortest path in a graph, weighted graph generally. And Dijkstra algorithm is, we know that, right, for the non-negative edges is used. Belmont and Floyd is for the allows the negative edge weight also. But here is the condition is there should be no negative cycle. In both we can see it here, this one and this one. And the difference between Bellman-Ford and Floyd-Vercel is it is the all pair shortest path this is used, and this Bellman-Ford is for only single source for shortest path. Means from one vertex we will try to find the shortest path to all other vertices. But this Floyd-Vercel is to all vertex, what is going to be the shortest path? It will give the last iterative that matrix will give the last, whatever you will get the last iterative matrix that is going, you will give you the shortest path with respect to all vertices to all other vertices. And Prism and Kruskal algorithm is to find the spanning tree, minimum spanning tree, MCST. So let me show you the next thing is the Dijkstra algorithm. So Dijkstra's algorithm is the
Can
algorithm
you
is
please
used.
go back, sir? This one.
Okay. So if you want to know the differences is written here: Dijkstra, Bellman-Ford, Floyd, and the Bruscal. This is used for minimum.
Which means in a particular cycle or within two vertices, sir.
Sorry, which one?
So the third one.
Third one is for all vertices to all vertices. Here the one whatever you will get the last iterative matrix, no? And if you want to suppose find the matrix in the last matrix, the vertex suppose 0 to vertex 5, the last matrix whatever it will give the minimum cost, minimum shortest path will give. The last matrix is actually for any, like for any vertex, it will give the, or let me write here. Let me show you to write. So this last matrix is whatever you will get the last matrix. In that matrix, like suppose the vertices are 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. These are some matrices. Vertices you have. So whatever the entry is, it is written here or here, you will get. So it will give the shortest path between the vertex this one to this one. Similarly, whatever the entry you will get, it will, or here is the, so this is give the shortest path between this vertex to this vertex. But Belmont actually give Bellman-Ford is whatever the last iterative matrix is there, that is give for only the single sort vertex for which you are running the algorithm. Like you said for 0 vertex, so 0 with respect to 0 vertex, it gives the shortest path. So whatever the entry you will get here, no, it will give the shortest path, but with respect to 0 vertex only. This is the difference between Bellman-Ford and the Floyd-Warshel algorithm. Got it? Am I audible? Am I audible?
Yes, sir. You are audible. Yes, sir.
Okay. So let me move ahead to the next slide. So the Dijkstra algorithm is here. The Dijkstra algorithm is used to find the shortest path from a fixed source vertex to every other vertex in a graph G. In fact, it is applicable for the weighted graph with positive weight. So yes, as we last time seen, it is only for the positive weight graph. It will not applicable for the negative weight graph. And okay, it is not applicable for the negative weight graph. Algorithm is start with the source vertex, suppose I is there. Okay, initialize the distance of the vertex I to 0 I, which is means here it says that once you started that algorithm. No, let me open it. The slide is here. Okay, so it says suppose you have the different color. Suppose you have suppose this is the graph if you have. Okay, so suppose this is the graph if you have. So the first thing in the Dijkstra is the non-negative weight should be, so or whatever the vertex you have, edges you have, the weight will be non-negative. And the second thing is it is a single source shortest path. So if you started from here, okay, so in initial time just give this weight, or that if you start the algorithm, no, so what is written is initialize the distance value of the vertex is for, if you started from here, so give it 0, and other vertex the value, what the distance value or weight value will give the infinite. Once you start the algorithm, you will give the infinite, means here whatever the weight will is there according to that, once you do the steps, you will update this infinitive thing to whatever the weight graph or the distance you are getting. Each time a new vertex is visited, update the minimum distance value of its neighbors. So each time you have to update the minimum value, so that Once you do that, we will see. We have an example. Okay, so this is the first question. An undirected graph we have. Okay, we have an undirected graph, weighted graph we have. Okay, and the question is this one. Find the set of all positive integers values of x such that if we use the Dijkstra algorithm, the length of the shortest path from the vertex A to the vertex J is less. Vertex A is here and vertex J is here. This one. So okay, this is the vertex. So it will be whatever the we want to find the value of x. So this is the age we have, and the weight of the age is this one. So what is going to be the value of x, so that the shortest shortest path from A to J will be lesser than. These are the weights it is written, and see, you can see that the weights whatever written here is always positive. So please everyone solve this. And in steps we will see what is going to be the answer.
Can you just give us 2 minutes?
Is that in this question not very?
Sorry, could you repeat please?
So do we have to solve now, sir, or something? Will you be taking the solution?
So please solve this one. I'm just giving time to all of you. And answers, please post in chat. And whenever you are doing the message, please direct message me. Can we start discussing the solution?
It's 2 minutes.
Sorry. Okay, so can we start?
Yes.
My voice is clear, right? Am I audible?
Yes, it's clear.
Okay. So in the first step, what we can do to find that what are the possible value of x? Here is the written the possible value of x. Okay. So what okay. So whatever the possible value of we have, we can like remove the edge B from the graph and then find the shortest path from the vertex A to the other vertices using the Dijkstra algorithm. Okay. So again, the Dijkstra is the shortest path to find from the single source to all other vertices. So what we can do, we can think it, we can think it as like just remove the B. So in the next step, we can see the solution. So start the vertex A as the source vertex and initialize the distance values to zero to vertex A, another value. So as you have seen the Dijkstra algorithm, when you initialize the algorithm in starting, we don't know the burning time. So that's why we can give the other vertices as an infinite value and the source vertex as zero. That is the starting point. So that we can give that is zero and the other vertices will give infinite. So the next step, like here we can see that as here is the zero and the other vertices, the shortest path, that means weight, mean to say. So here other vertices will be given as the burning time, as you have seen uh, in the in the video lecture. So you can give as a infinite. So you can see that all others are infinite. The next step, So using the Dijkstra algorithm, update the distance value of each the vertex in the graph that is adjacent to A, which is the initial. We are initializing the algorithm from A. So whatever the adjacent or neighbors vertices we have, right, and the distance we can see in the next step, that one. So this one we can see. So the adjacent vertices we have B and D. So update that. So like here the distance or the whatever the update we will do, that is 1 and 2 here. This is the algorithm. This is the process to do the Dijkstra. So in the next step, now update the distance value of each of vertex in the graph which are neighbors of D. So which are the neighbors of D? Update that. So means here in the previous one, vertex A. So update whatever the neighbors with the minimum weight. So we can see that here is the update we did. Okay. And this one, and the next step is update with the neighbors of B. So we have updated this one, which is B is here. So this is 1 and this is neighbors is 2. So this is weight 2. So by this way, in the next step, it will be more clear. Okay. In the next step, what will be the minimum distance now for that? It is going to be, so update the distance value of each of the vertex in the graph, which are neighbor of B. So whatever the neighbors of B, update that distances. Okay. So it will be like, if you update this, this is will be from B, it will be 2 and 4, which is become 6. Or by this way, if it will go, so it is 1 and 5 and then 4. So it is the maximum value, which is 998, but the minimum value we want for to update, because shortest part we want. So this will become, that's why 6. Is it clear till here? Please let me, because all of you are very silent. Is it clear?
Yes.
Okay, so now update the distance value of each of the vertex in the graph, which are neighbors of C. So neighbors of C is with the distance value of each of the vertex in the graph, which are neighbors of C. So neighbors of C is this one and this one. So here with the minimum weight, it is going to be here 6 and 3, 9, and this is going to be 6 and 8, 14. See, this is the update we have, but by this route we will go. That's why this is the red, in the red color it is given. Now in the next step, update the distance value of each of the vertex which are neighbors of E. Now for the minimum value we are going, so with respect to this one, update. So this one will be updated, the minimum value now 9 and 4, 13. So it should be here 13, but it is not updated here. Okay. It should be 13 here, and this is 9 and 1, this will be 10. This one is updated. This will become 9 and 6, this will become 15. But this red color is for the minimum value. That's why it is in the red color. Okay, now for the G updation we will do, for the G updation we will do, then see that now update for H will be what? 12. So this will be 12. By this route we are going this, and this. Now for the F also will be update here, so 12 will be, here is 9. Okay. Now next step is update for H, neighbors of H we will do. So update for J, it will be 13, and I will be also 13. As here 12 plus 1, here is 12 plus 1. So updates we did here. Okay. So the length of the shortest path from the vertex A to vertex J is obtained is 13 we have. Okay. But it is given that the length of the shortest path from the vertex A to J is less than 13. So here is, we want less than 13. But if we gone through with the minimum weight, this route, whatever the green route is given, we got 13. But it is in the question, if you see that, it says the less than 13. Means surely then what it means, then surely there will be a weight, there will be an H which give the weight mean less than 13. So that's the plan came here for to adding VE, which we don't know. That's why the value X is given. So length of the path for B to E is 7. If we assume that, if we assume 7 now, if it is lesser than that, okay, it is 13, no? So if you add others value like this one and this value and this value, this value and this value without adding the value of x. So this value is 2, this is 3, this is 5, and this is 6. So if we add here the age, which we don't know, so and if we give the value 7, then it will be 13. Okay, so that means if x value means we got whatever the x value is 7, if it is lesser than then the if we go with by this route, by this way, we go by this way, this one and this one, and okay, by this way, then this, then the weight will be for J is going to be minimum. So that's why if you see that weight of B is lesser than weight of BC plus weight of CE, which is less than 7.
So this
The next is
path is we have taken as 13, and how do we know this is the path followed so that the value, the distance, shortest distance of J is 13?
So yeah, that's the thing. So here is if you follow this path, okay, if you follow the whatever we have previously did, if we follow that previous path, this
So it can go
by
from A
this
to
path,
B, B to C, and C to H also. C to H and H to J, right?
C to H. If you go C to H, the weight will be max.
Okay.
So that's why
Similarly,
this path.
also
So that's
C
why
to
the
E and E
algorithm is.
to H also, and H
So
to
that's why
J.
we are doing this algorithm. That's why the extra algorithm says go with the minimum weight route.
Yes.
So by this way, if we go through, still the weight we got 13, but we want less than 13. So then how we will go? That means there should be an edge by this way or by this way, something there will be.
Yes.
So if you, but here is this is the route which is minimum. So surely will be an edge will be added directly so that it will be minimum. So that's why
yes.
you see that is the 7 is going to be, and the rest all the 7 we got because of you add this one, and this one and this one, which is 6. And if we give the weight x, sorry, here is this age weight 7, then it will become 13. But we want less than 13, that means x value should be lesser than that. So that means here is x value is lesser than that. Now you can assume that the values is going to be 1 to 6. So that the weight will be minimum. Now here is 1 to 6, the value is going to. By this way we can think. Okay. So let's move to the next question.
So can you just show the solutions? So the options.
Sorry.
Can you just show the question?
Okay, options. So options is going to be this one: 1 to 5, 1 to 6, 1 to 7, or 1 to 8.
Yes, sir.
So options is going to be now 1 to 6 only.
Exactly.
Yes.
Okay. Now let's move on to the next question. So here a company has a branches, okay, in each of the 5 cities, C1 to C4. Okay, 5 cities we have. If okay, the fare in the thousand of rupees for a direct flight C1 CI to CJ is given by the I to jth entry in this matrix. In the 1000 value, these values are in the 1000. Okay, in rupees it is given. Okay, and direct flight it says if you here is suppose I and here is J, or 0 1 2 3 here is, and 0 1 2 3 here is. So this is the price of direct flight. So these are the price of a direct flight is given. Okay, in the following matrix. Infinite sign indicates that there is no direct flight. Okay. Now in the next step, the question is an employee of that company wanted to travel from city C0 to C3. Okay, C3. Okay, if she travel by the cheapest route possible, then the total fare she paid for the flight. So see, it is already given. Now we can see that here the prices, or if you draw the graph, it will be you can see that you can see it here that there is no negative weightage also, and it says that the cheapest route possible, and that is the the shortest path is actually uses here. So the question is asking what is going to be the paid money per flight journey. So please everyone solve this problem. If you are not getting, please let me know if you are not getting this problem. So how we can do, we have to form this, we have to form a graph for this one, and then we can use the Dijkstra. Okay. Please everyone, if you are not getting, please let me know the question. And as a hint, first you have to find the graph of the using the adjacency matrix, and the entries you can think here. No, this is 0, 1, 2, 3, 4. This is 0, 1, 2, 3, 4, and find the graph. Once you find the graph, you can easily do that using the Dijkstra algorithm.
So do we have to draw the graph and then?
Okay, who's next?
Without that, we don't know the Dijkstra algorithm. No, so this is, if you know the Bellman, you can do that. Also, Bellman will also apply.
Yes.
So can we discuss the solution?
Yes, sir.
Okay, anyone solving? No one have posted the answer. How much amount she paid for the flight journey was? Or need to take more time?
No, sir, you can do the solution.
Okay. So here is the if you can see the first in the solution step, we have to draw the graph that will still represent the given adjacency matrix. So the graph we can see here, we have the adjacency matrix is this one. We can indicate the here vertices, and the graph we can represent like this. Okay. Now, as we have already, here is, you can see here is the non-negative weightage is there. So, like, please let me know how many of you have drawn the graph of this. All of you have tried this or just looking here? Anyone have drawn this graph?
Yes, sir. I have drawn this graph.
Yes, sir.
Okay. Okay. Now in the next step, we use the Dijkstra algorithm as there is no negative edge. So we can go, if there is a negative edge, then we have to go with the
So
Bellman
can you
4,
please
but
go to the previous slide?
yes. And also we want to find what? We want to find the paid amount from C0 to C3. How much she will pay, minimum amount. That amount we want. So from this city to this city, how much she will pay, or what is the charge she paid for the flight. So use the Dijkstra algorithm, and we want from C0, no, from C0 to C3. So we can use the we can start the algorithm from C3. Sorry, C0. So here is, we can, as the algorithm is there, just give to 0 and other vertices weight or the distance you can give as infinite. We don't know, or in the other way, we don't know the burning point or burning time. Okay, you can think with the here again. This is the source vertex, which is a burning. You can give it to 0 and other vertices at the, we don't know the burning time, so that's why it is given infinite time. Okay, so this you can think as like this, or you can charge. So this is the sign of doing the algorithm. So you can give the infinite sign. Now we'll do the update. So here from C1, so minimum weight side we will move. We will move to the, yeah, somebody's have posted. Okay. So minimum weight side will start moving. So that's why we will not move to this C4, this side, because cheapest or minimum amount C paid. So we will move to C1. Okay. So this is will be update will be 2 easier from infinity to 2 it will be. Now again the next step is the, now we are algorithm is doing, no, so from this way and this side, if you from this is Dijkstra is from single source to all vertices. So from C0 to C4 is what? It is 4, and from C0 to C1 it is 2. Okay. Now in the next step, from C1 to C2, which is this route will go. Okay. By this route, by this route we will go. By this route it is going to be, now the update, see that it is infinity to 2 and 3, which is 5 here. Okay, and this is again it is still 4. So the next step here is from, now from C2 to C3. If you go along this is 6, and if we go along by this way, this is 4 and 6, this is 14, but we write in the minimum. And if we go along like this, C4, and then this way, this is 9, it is going, so going, but we are going through the minimum, so that's why this is 5 it will be. So C0, C1, C2, and then C3. So this is 6 here. The
So do we have to check
distance
each
we
of
can
the
say.
vertices?
Sorry.
Do we have to check for each of the vertices and then come
Yes,
to
yes,
conclusion?
yes. We have to check, and you have to check, and then we have to write the minimum. So finally, once we do that by this rule, which we got 6 here, so it is written in the thousand, so that's why it is 6 and 1000. We can write to 6,000. It will be. So hence the total fare paid for the flight journey by traveling the cheapest route is 6,000 rupees. Okay. Now in the same information, which is similar information we had, but in the
Can you just go
question
to
is
the
different.
previous question?
Yes.
The questions.
Sorry, question is. So I can tell the question. The graph we had this one. What is the minimum? What is the minimum call or minimum weight from C0 to C3? What is going to minimum weight from C0 to C3? Or even C2 to C1 also, the extra is we done, no? So C0 to C1 is 2, C0 to C4 is 4, C0 to C2 is 5, C0 to C3 is 6. So this is the extra algorithm is for the minimum shortest path. Sorry, minimum I'm saying shortest path for the
Please
shortest
show
path.
the question, sir. Then I understood the solution.
This is the question.
Yes, sir. Got it.
Okay. And the next, this is the next question. But here is, if an inspection, okay, team member wanted to inspect all the branches of the company, starting with C0 and ending at C3, visiting each branches exactly once. Okay. Then which route should be choose in order to pay minimum fare for the flight? Okay. This is the question we have. Okay, we have the company. A company has branches in each of the 5 cities, C0 to C5. The fare is in thousand we have. Direct price CI to CJ as this matrix is representing. Okay, in this matrix we have the information, and the inspection team is starting doing the inspect the branches to all companies. Start from C0. C0 is the source vertex, and C3 is the ending. Then which route should be choose to in order to pay the minimum fare for the flight journey? If your route is like this, then you can put the in chat is which route is going. The case center answers. So please remember that inspection team is actually visiting the all cities branch, and she want to know that, or they want to know which route when in inspection, okay, inspection, which route will give the minimum fair flight. So can we start discussing the solution?
Yes, sir.
Yes, sir.
So the graph will be as previous one, so not going to give much time here because we have drawn. Once you draw the graph as the last time we did, to draw the graph, it will be the similar graph. It will be now the inspection team member to start from C0 and end at C3. In between, he has to travel C1, C2, C4 at least, because here they are traveling all branches, all cities. So they have to travel C1, C2, and C4. Try to explore all possible paths starting from C0 to C3. So we want a route, right? Route, right? Minimum fare with the minimum fare. So try to explore all possible paths. So either this way, or by this way, or we have three, no, by or by this way. There are 3-4 ways we have, okay? Which is also needed for at least we have to see the all branches, which pass through the all branches. I mean, by this way, or by this one, and then this one, and then this, and then this, and then here. So identify the paths that contain all vertices. There can be more than one. Okay, so there is, so by this way,
So here do
routes
we
are
have to
here.
use the extra or?
Yes.
So here is the Dijkstra is not Dijkstra. Here is you can just need to find the route only.
So we
which
just
gives
need
the
to add
minimum.
up the values and just
Yes,
find out.
that means here means find the possible routes like this one, this one, this one, and this, or this, and this. Have to go all cities and the possible paths. So you can see that here is 2 paths we have with the, we have to go all cities and with the possible paths we have. So these 2 paths, as here the green one and this red one. And now calculate the weight here for the C0 to C1. So for green one, for weight is 20, and for the red one, the weight is we got 21. Okay. So here is, hence the inspection team member should choose the green path as it gave the minimum weight 20. Here is not that extra algorithm is done, it's just finding the, you have to find the route, all possible route, and then find the weight and which give the minimum weight. Okay, minimum length path or minimum weight. Is it clear? Is it clear? No, yes, no.
Yes, sir.
No,
Yes, sir.
Okay, so the next problem, let's solve the next problem, which is the first we'll see the Bellman-Ford algorithm. This algorithm is used to find the shortest single source path to every vertex. Okay. The fact is here that this algorithm is applicable for the negative and positive both edge, and but the not negative cycle. So this not allows the negative cycle. It is applicable for both negative and positive, but not allowed the cycle. Negative weight cycle. Negative weight cycle means what? We have seen, if you calculate, suppose if you have a graph, okay, But in
So
that
can
you
you
have a
please go to
cycle.
the previous?
Sorry, yes, I am just doing this. So let me tell
Previous.
you. Yeah, I will please let me explain that what is the negative cycle is. Means suppose here -2, this is -3, and this is -4. Or here exactly you can see that here is -1 also, or 1 itself. Now if you calculate the weight of this graph is going to be -1, which is a cycle and with the negative weight. So but we don't want this in the Bellman-Ford. Okay. Now algorithm is DJ, where if you have remember that algorithm, so there is a sign DJ is the minimum distance known so far to the vertex J, where it is from which place it is initialized and which place is you are going. Okay. And initialize from D0, or if you started from if J is equal to 0 so it will be D0. Otherwise, whatever, and if it is and for the other value, it will be infinite. You don't know that exactly, so you can give other value as infinite and starting as a 0. Repeat n -1 time. So as you know, we have n vertices, then we have to, there are n -1 edges. Okay. If you do repeat this algorithm n -1 time. So if it is more than n -1 time, that means it will be repetitive, because once you have checked all edges. So that's why it will going to be repeat the algorithm. So that is the stopping point. So you have to repeat this algorithm for n -1 time. So what is that? Repeat this algorithm. What is that? For every vertex j 0 to n -1, for each edge edge jk belongs to E. Okay. For every edges we have to do that, and we have to do what is that? Update. Dk is going to minimum of dk and dj plus weight of jk, like some value it will be assigned, and weight of, once you update that and choose the minimum one. So we'll see once we'll do the algorithm. Let me move ahead. So suppose while doing this problem, okay, we'll see the algorithm also. So here, what is the value of x? Can use the Bellman-Ford algorithm to find the shortest path from source vertex 0 from this one to every other vertex in the graph below. What is going to be the value of x, so that for other we will have to use the Bellman-Ford, and what is going to be the value of x? Which of the following can be the possible value of x? Okay, this is an interval. Okay, this is not in pair. This means that it is an interval from -1 to infinite or -2 divided by 8. Please everyone solve this problem. So this is the for the when we can use the Bellman-Ford algorithm. Okay, we have to choose such value of x so that we can able to apply the Bellman-Ford algorithm. What are the conditions we have? It says that it doesn't have any negative cycle. So that means we have to check that we are able to. So this problem is to when we can use the Bellman-Ford algorithm. Not asking for the Bellman-Ford algorithm, it is asking the condition. And what are the condition is that only one condition we have, it does not contain any negative sign.
Negative edge means the value of, like, for example, 0, 1 is minus.
Sorry.
So negative edge weight means For example, the value of connecting 0 and 1 is -6.
0 and 1 is -6. Here is 6 is given,
For
negative 8
instance.
is.
Yes.
Yes.
Can you show the algorithm for a moment?
Okay, so algorithm is, here is not algorithm we will use. Here is one condition we will use to solve this problem. The condition is it does not contain any negative weight sign. Okay. Because this problem is asking so that here we can use the Bellman-Fold algorithm. We want such value, not exact value. Here is some interval values given. We want such value of x so that we can use the Bellman-Fold algorithm to find the shortest path.
So can you just move to the previous page, sir? Just a minute. Thank you, sir.
So I have seen somebody posted the answer. So let's discuss the solution. So here is only many times I said, right, you have to check the condition. Here is recall the Bellman-Fold algorithm is not applicable for the negative weight cycle. Notice that after n-1 iteration, the shortest path value does not converge. Why? Because if it is the negative weight, then the shortest path values does not converge it. It is if it is there is negative cycle, it will always give the minimum values. That's why it is that means here the after n-1 time the shortest path value does not converge. That's the meaning here. Once you do start the many times making the matrix, for at least for after n-1 iteration, it will not convert the minimum value. So here the note is that to say this is 1, from 1 you can give go 4, from 4 you can go 2, and from 2 you can go 1, can reach to 1. So here is a cycle is happening. Okay, here is one cycle is happening here, but the condition is needed. We don't want negative cycle. So now let's add it here. This is 7. We have the value. This is 7. So whatever the values you can give, which should not be lesser than -7. Now, if it is less than -7, then it give the okay. It is a okay. So if it is less than value -7, then it will give the negative weight cycle. That's why the value should be always greater than -7 at least. The all value, whatever the value from 0 to infinity, any value you are going to x, but it should not lesser than -7. If it is lesser than, then it will become the negative weight cycle. Therefore, you need to just take the value greater than -7.
Excuse me, sir.
Yes.
Can this value be equal to 0, sir?
Yes, it can be 0. Yes.
Okay.
It can be 0. If you give 0, still if you count the weight, it is the weight of the cycle is 7, right?
Sir, doesn't it mean that all three sides will collapse to one side if cycle is 0?
If cycle value is 0.
Yes, sir.
So here is not mean to, it can different scenario also. If we are giving the weight or cycle values 0, but it can be in different scenario, not only for the collapsing kind of thing.
Okay.
It can be different scenario. We don't know exactly that.
Okay, but cycle can be 0, but not negative.
not minus. Yes.
Okay, okay, sir. Thank you.
So Uma have doubt in the previous.
Yes, sir. Sir, I assume that you can revisit the city. So I just wanted to check. So the assumption is that you should not revisit the cities, is it? From C0 to C3, that question, sir. Sir? Are you able to hear me, sir? Hello.
Sir,
He has lost the internet connection.
Am I audible right now?
Yes, sir.
yes.
I just got disconnected. So here is the problem. Consider the graph G shown below. Here is this one. Suppose the source vertex is 0. From 0, we want to start. We need to perform the Bellman-Foyle algorithm up to 3 iterations. Okay. So this is an example is there. This is not problem. So this is an example is given that. So how we'll proceed. So that is the Bellman-Foyle. 3 iteration we want. So as we just said, give the initial initial point is 0 value and rest all we don't know. You can give the value or sign is infinite. Okay. Then the second iteration, what is that? So here is from 0, you can see the update the second in the from 0, we can do here is this way is 7. Oh, sorry, this vertex 7 is, this is going to be 6. So we can see it here. Here is the value is going to update from infinitive. This is going to be 6. And for 4, we have, for 4, we have here the value is 4, you can see, and for 1, it is going to be 10. Okay. And the next step, which is going to be here, and the next iteration, in the next iteration, whatever we have update, we have no, whatever the vertices we reaches, from there to next step we can go, like here to this one, 6 is vertex is, now it will be 4. Now we can see we are able to reach from 0 to 7, and then 6 is going to be 6.
So
So
can
you
you
can
just
see here
explain
is
how do we
update
do
is
for the third iteration, sir?
third iteration, this one,
No, sir, the third time, yes, sir. Like, how do we?
this one.
Yes, sir. I'm not sure of the graph, and also not the graph matrix.
So using the graph, only the graph we are doing, no? So first time we got this one. Okay. First
Yes.
time we got from 0 to 7, 0 to 4, and 0 to 10. These are the updates,
Yes,
you can
sir.
say 1, 4, and 7. Now in the second, once you do the next step, so from 7, where we can reach? From 7, we can reach only 6, right?
Yes, sir.
So that means what is going to be weight for the vertex 6 is now the whole
4.
vertex from 0 to 7. This is going to be 4. 6 to, now see that if you add, this is 6, this is minus 2, it will be 4.
Yes, sir.
Okay. Now from 7, we cannot reach any other vertex, only reach to 6. Now what are the other vertex we have? 1. In the first one, we have 1, 1, 4 and 7, right? So now let's check for 1. From 1, we can reach only 2. So let's update the weight for 2. So which is going to be 10 and 1, 11. So for 2, see that this is 11. Okay, now we have for 4, we have also in the previous one, we got the weight for 4. So from 4, we can reach to other place? No. See that this is
No,
only
sir.
the incoming edges we have, in degree we have. There is no outgoing edge. So that's why there is no update. So only 2 update is there for 2 and 6, which is
Yes,
in the
sir.
red color. Now the next iteration you can do. So in the next iteration from where we can do, from 6 we have to do, from 2 we have to do, from 2 we have to do, and also from 6 we have to do, from 2 we have to do, okay, and from 4 it is already done. So from 6 we do, so from 6 we can reach 3. So see that's why we can calculate the edge, which is 4 here, and then 4 it will become what? What it will become? It will become 0. So see, if you see that 3, it will be, now not -4, this is for 4 and this 4. This 4 and this 4, which is 8. So for 3, we can see the update 8. Okay, now for 2, we check. For 2, we can reach only 5. Okay, for reach, so 5, for 5, we have to do update. So for 5, if you do update, so by this, which route we can go? We can go here. So this is
7, 6,
from
5.
2. Sorry, which route it will give? 7,
0 to 1
6,
to 2 to 5, sir.
0, 1 to 2,
2 to
and
7,
then
7 to 6, 6 to 3, 3 to 4.
no. So if you see the weight of 5 is 1, but how? Okay, this is correct. Okay, this is fine.
0, 1 to
So
5.
0, 1, 2,
So
5, sir.
0 to 1, 1 to 2, 0 to
2
1,
to
1 to
5.
2, which is 11. Now from 2 to here directly, which is 10 weight is given, -10. So that's why the
Yes,
weight
sir.
is going to be 1. And any other vertex? So these are the previous one vertices we did. So 3 updates is done here. So this is an example. You see, this one is so there is a problem
sir,
based on that.
For
How-
7, for 7, how it is 3?
Oh, yes, sir.
For 4,
For 7, 7.
For 7, how is it 3, sir?
sorry, for 7, for
This is
4
11
you are
man.
saying, for 4 is this one.
I think 0
This
to
one
1,
and
1 to
this
2, 2 to 7.
1 to 2,
Yeah.
2 to 7.
Yes.
This is 11 minus 8.
Okay.
By
Yes,
this route,
sir.
because we have to check from route from which places we can go. From 2, we can go 7, and from 2, we can go 5. I just forgot to update this one. There are 2. So that's why which place you are checking. Okay, suppose you are checking 3. So from 3, we can go 2. From 3, we can go 4. So according to that, we have to update. Okay.
Yes.
Now let's do what are the values of D3, D5 and D3, 4, 5. What are the values you have? Please do the next 2 iterations. We have did till 3. Okay, so we have 7 vertices, no? Next 4 iteration we have to perform. Sorry, 7, no? So 3 iteration more we have to perform. which you have completed. Yes. Nice to see. Please, everyone solve this.
1 minute.
Yeah, yeah.
Yes, sir. I think you can start.
Yes, sir. Start.
Okay, so let's do now. So now till here, I think we did. Now in the next step, we can see, no, till here we did, no? So fourth iteration and fifth iteration is here. 4 to 5th. Previously it was 1, 4, 3, and now from 6 is done. From now from 3 we have to check. So from 3 we can reach to 2 and 4. So see that the update will be for 4, it will be for 2, there will be no update because it is 20 weight is given. So for 4 update will be what? Sorry, for 4 the update will
Can you
be,
please take this
still
slowly?
it is
sir?
coming.
Slowly means in
Sir.
detail.
So till which iteration we have completed? I think this till this one, no?
Yes, sir.
Till this one, in the previous one we have completed. Now next iteration, what we have? So till 3 we reaches, no? Till 3 we wrote till 3 we wrote 8. Till 3 we wrote 8. And here is till 3 we 8 is wrote, 4 we have already, 4 we have directly. Okay. And 5 is already, we have checked that it is going to be 1 because this root, if you go by this way, it is going to be 5 for 1, it will be. And 6 is, for 6 is this root, if you go already, we have checked, so which is going to be here. Now here is from 4, 4. Now there is the update. So from 6, how we can go? So if you check that, we can reach to 6 from 5. So if you go by this way, this and then this. So see that this is 10, this is 11, this is minus 10, so 1, and this is 6. This is 2 we have, no? Okay, this is 2, it shows. Previously, so 2 we can reach here. We can reach 2 by this way or this way. So from 5, so 5, what is the 5 we have? 5 value is 1. So
I
5
think
is
5
here
to 6,
1.
sir.
So from 5 to 6, if we go that, it is 1, 1, 1, and this is going to be 2, but here is 1 written. I think we are missing something.
Can you directly go from 5 to 6? Sir?
So if you go by this way, okay, this is 10 and this is 111, then this is 10. So this value is give 1 and this 1 and 1, this give value 2. I think there is a error, I think. Right here, the value will be 2, right? Or we are missing something, only we can reach to 6 is only this way, no? Or
Sir, I think 0, 1, 2, 7, 6.
0, 1, 2, 7. Okay, if we go by this way, okay. This is 10, this is 1, 11, this is 3. Okay, by this route, if you go.
1.
Okay, here is the by this route. If you go, then the update will be 1. Okay, we didn't check. So only we are checking by this way and this route only. But we can reach to 7 or 6 by this way. But the route, okay, for 7 we have already. For 7 we have. 3. Okay, for 7 we have date 3, and from 7 to 6. So we have to check by this way. Okay, from 7, now 7 to 6 is 3 minus 2, which is 1. So okay, that's why it is going to be 1. Okay. Now in the next step, now we have to iterate the next. We have to do in the next iteration. So here is all the 1 for it is previous 1, 2. Now if you see the 3 is here. So which root will go, so that here is previously it was 8. So we can reach to 3 by only 6. Yes, from 6 we have, so 6 value is here 1, and 6 value is 1 here, and this is 4.
4.
This is 4. That's why the update will be from 8, which is previously 8. Now it will be 1. And the rest all it will
How,
be the
sir? Can
same.
you just explain? The fifth iteration.
See,
how
we
shall I
reaches, see 3 we have, from which vertex we can reach 3? Only 6, right?
6.
And what is the value 6 we got? 1, right?
Okay.
Now this 1 and this 4, this will become 5. That's why this value is 5. And rest all, if you check, it is going to be the same. Now from 6th iteration and 7th iteration is written here. So now previously the 3 value is 5. Now check 4 values, because we can reach the 4 only from 3. So this is 5 we have, and then this minus 3, which is 2. So previously the 4 value, the 4 vertex 4 we can reach from 0 to directly, but also we can reach to from 3. So 3, the vertex weight is here 5 we have, and this is minus 3. That's why the update will be from 4 to 2.
Yes.
And from any other place from 3 we cannot go. We can go to here, but the weight, if you see that, it is going to be very large, 20. That's why there is no update for 2, but only update will be here for 4. Now if you do the 7th iteration, in the 7th iteration it will be what? 4 is done, 5 is done. So it will be exactly the same. In the 5th iteration, it is the same. Now you can see it is converging, value is converging. So if you do the iteration more than 7 or 8, it will still the value will be same. So, but we need only the n-1 time, which is 6 time we have to do the iteration. So there are 7 vertices. No, only 6 time we have to do, but 7th time, if you check that, this is for the checking only. The value is actually converging.
So we're
Now
increasing
if you check the
each
value,
time.
which is,
Do we have to check from the previous value in which the value was changed, sir?
yes, without that, yeah, that's why. Without that, how we will be sure that we reaches to that point with the updated value?
Yes.
Okay. So let's do the next problem, which is Floyd-Warshall algorithm. Okay, Floyd-Warshall algorithm is for all pair to all pair shortest path it keeps. The fact is, again, negative or positive is allowed here, but no negative cycle should be. Now here is SPK is actually is the length of the shortest path from the vertex I to vertex J using vertices is 0 to 1 to k minus 1. Here is whatever the SP superscript k is here. This means tells you that from 0 to k minus 1 vertices. So if you want to find the shortest path from I to J, but it will use the vertices 1 to k. Either it could be 1, either it could be 2, or any combination of it, or the whole vertices, even the whole set means 1 to k minus 1. Using those which is give the minimum shortest which give the shortest path to reach I from I to J. Okay. For example, here is if we compute SP3, okay, here is k value. If you see that SP3, it means we need to find the shortest distance from any vertex I to vertex J via the vertices 1, 2, 3. Okay. If no path between vertices, then simply the distance is going to be infinite. Okay. Now, for example, this is an example. Use the graph below. This is the graph. Use the Floyd-Warshel algorithm. Let's see the what are the values of SP0. SP0 means 0. If you substitute here, that means 0 k minus 1 is there. So k minus 1 which is minus 1. So that means there is no update, or exactly whatever this graph is given, no, the adjacency matrix we need to write. That means SP0 is exactly the adjacency matrix of this graph. Okay. So adjacency matrix, if you write, so whatever here is weight is given, you will write the weight, and if it is not, there is no direct age, then that value is going to be infinite.
Why do we say it is a weights?
Sorry.
Is it because the value of k is 0?
So value of k is 0. That means how many vertices it will go from?
Just one.
Not 1, even -1 is given, no? K minus 1 vertices. That means -1 vertices
Okay,
it says.
okay.
So there is no meaning of it. That means it says actually SP0 is exactly the adjacency matrix.
Yes.
Okay. Now let's see what are the values of SP3 we have. SP3 value is going to be what? So let's see that. So it means we need to find the shortest distance from the vertex I to vertex j via the vertices 0, 1, and 2. Here is 3, that means 0, 1, 2. Now let's do that. Let's find that. Let's do the entry here from 0 to 0. So from 0 to 0 is generally what? In place of 0, we'll write what? Why it will be 0. So in place of that, infinity will be from 0 to 1. 0 to 1. So it's already says 0 to 1. We need to go with the 0, 1, 2. So it is going to be exactly the same. 0 to 2. 0 to 2. Where is 2 is here? So here is, if you see that, here is 0 to 2. So there is no root, no? 0 to 2, there is no place to find, there is no way to find exactly at 0 to. Okay, here is I think here is a mistake. Is from 0 to 2. If you go with 0 to 1 and then 1 to 4 and then 4 to 2, then what is going to be here? Here should be 4. Here should be.
So, but it should
0
pass
to-
to the should pass to only 3 vertices, right? So
No, even it should pass either from 0, either from 1, either from 2, or 0, 1, 0, 1, or 1, 2, or all 3, 1, 2, 3. Any of that.
So via vertices 0, 1, 2 means it must pass only through these vertices, sir.
No, here is, if you see the algorithm. Okay. Is the length of the shortest from vertex I to using the vertices 0 to 1, 2, 3, k minus 1.
Yes, sir.
Okay. We have to find the such path which uses the vertices 0, 1, 2 like this. So
So
here, like, if it.
hello.
Yes.
Sir, when we use SP0, that is, we are finding from zero vertex to every other vertex.
No, SP0 means not 0 vertex. SP0 means exactly the adjacency matrix.
From 0.
Not from 0. Here is for all vertex to all vertex. No, so that means
all
here
vertex.
to all vertex means that is not from 0. It is the way. Here is the SP0 means you are passing through the vertex 0, 1, or 2, or 1, 2, or whatever the possible combination it has. So here should be 4. If you check that here to reach, if you want to reach 4, 0 to 4, then this way, if you go by this way, 0, 1, and then 4, so this is going to be 0. Okay. Now, if you want to go 1 to 0, 1 to 0, so there is no root, so that's why it is infinite. 1 to 1, it is again infinite. 1 to 2. 1, 2, 2, there is no root. So 1, 2, 2, we have to go by this way and then this way. If you 1 to 2, if you say that, this is going to be 1, 2, 3, 1, 2, 3. 1 to 3 if you so 1 to 2, 1 to 2. So 1 to 2 is only showing this root. So here is actually showing the infinite. So it should only pass through that vertices is, just a minute, let me check once.
The via vertices 0, 1, 2 means are they representing the name of the vertices or the number of vertices through which it can pass, sir? Like irrespective of the name.
So here is, for example, if you compute SP, it means we need to find the shortest distance from any itinerary via 0, 1, 2. It should be via actually, yeah, this is actually this is an error. This here is should be there should be updated one, because via means it is not saying you cannot go with that. It says that it is, yeah, you can go with that.
So we can proceed with 0, 1, 2, 3 only.
No, not 0, 1, 2, 3. Yeah, 0, 1, 2, either it can contain some other vertices also, but at least from 0, 1, 2, 3, you have to choose at least one or at least all three, or 0, 1, 2, or a possible combination, but it should pass through only that. Means pass through that and some other vertices. I mean, like 4 also can possible, 3 also can possible. Okay.
So
Via
how-
is written, no? So
I'm confused in SP3. I can calculate SP0, but I'm confused.
suppose to say that, for example, let me show you that. Okay, this is for SP0.
Yes.
So this is, suppose you want to calculate 4. And 4 to 3, if you see that 4 to 3, see that 4 vertex 4 to vertex 3. Okay. So
Okay.
what is the root now? For 4 to 3, it is directly given 3.
3.
It is not using the value 4 to 3. It is not using the value which is shortest by which pass through this one. So this is by this route. If you go this it. So see, it should be here. It should be here is, I think this slide is an error. It should be like this. From 4, we have to go with at least any one, 0, 1, 2. So it will go from here to this, and then this, and then this,
Then 3.
and then 3, not direct one. We have to use these vertices.
Okay, one of them, or
So any of them
or-
must pass through these vertices, right? Like for example, if you go from 4 to 3, it has to go from 4 to 1 to 3, right? Sir?
So if you go with here by this way, 4 to 2 and then 0 and then 1. So this is how much it is. This is 4, this is 0. So 4, 0. So this is, so here is 3 is given. So it is actually also it is given by this
So
way.
it has to go through all the 3 vertices.
Not all 3, any of them also can possible. So but we
Yes.
have to choose the minimum one. So if you go with this way, 4, okay, if you go like this way, 4, then 2, and then 1, and then 3, so it give maximum, right?
4, 3,
It
7.
give the
and
4
9.
and then 3, 7, then 9. But
Yes.
if you go with this one, 4, and then 2, and then 0, then 1, then 2. So this give the value 3. So that's why it is here 3.
Yes, sir. Yes, sir. Exactly.
Okay. This is the mean of, okay, you have to use any of them or like that.
And sir, when we have to calculate SP5,
So can you explain this adjacency matrix again?
Sorry, adjacency matrix.
Yes, so can you just explain this again, sir? Especially
So here is, and for the let's do for the 1 itself. For 2, if we check that for 4 to 2, so 4 to 2 is here. So directly it is 2 is given. So 4, 3 is the best one is for giving through, like which we will use the matrix. Okay. And other entries, if you check that for like from 3 to 4, if you see that 3 to 4. 3 to 4. 4 we can reach. 3 to 4 if you go, so there is no outgoing, no?
Yes, sir. That's why it's infinity.
We can
That's why it is infinite. So there is no outgoing.
Can you
So it
just
is going to
explain
be
2 to
infinite.
Hello,
2
sir.
to 1 and 2 to 3 alone, sir?
2 to 1. So 2
2 to 1, 2
1.
to 3, 2 to
Now,
4.
Sir,
okay, so
minus
2 to
4.
means here. From 2 we can go 2 to 1 is directly 3 is there. So 2 to 1. Okay, so see that 2 to 1 is here minus 3. So but
Minus
if you
4
go
plus
direct to go, so if you go like this, 2 to 1, if you go like this, minus 4 and then 1, then that's why the weight is here minus 3. That is not direct one. We want the shortest, no? We have to choose the short minimum value.
Yes, sir.
Sorry, minimum. So that's why this is going to be minus 3. 2 to 0, if you see that 2 to 0 is exactly minus 4, it is the direct edge is
So
there.
and 2 to 3 and 2 to 4.
And 2 to 3. So if you go 2 to 3, so if you go by this way, this is 5. But if you go by this way, then it will give the minus 1 value. Minus 4, 1, and then 2. This is 3 and minus 4, this give minus 1 value.
Yes.
And 2 to 4 is 2 to 4. So 2 to 4 is by this way. If you go this one, and then this one, right? This one
Yes, sir.
and
got
this one, and then this one. This is that's why it is going to be minus 4.
You got it, sir.
So this is the process. So you will use, like, you can use any of them. So I think there is an error also. Something is there. That's why it is like here is for 0. If you say, see that for 0 to 2, 0 to 2, 0 to 2 to reach here is 0, then this one, and then this one, and then we can go. In between we can test. 1 is coming, no? So it is going to be 4 is to be there. But here is infinity is
Must be
given.
4. 0 to 2.
Yeah, it is some error is, I think so. So this is an example. Let's do with this problem. This problem is not, it will not take much time. What is the SP4? SP4 means we want to find for this graph. SP4 means you have to find the graph which pass through, or we have to find the shortest path which pass through 0, 1, 2, 3, 0, 1, 2, 3 till 3 also. Means 4 minus 1, 3. Means either 0, either 1, either 2, or 0, 1, 2, or 0, 1, 2. What are the possible combination is? So we want to find, we have to find the adjacency matrix for SP4.
Taking 4 vertices.
Taking a 0, 1, 2, 3. 0, 1, 2, 3. Taking 4 vertices.
Yes.
So in this problem very easily. Only if you take one vertex, no, using that you can verify easily.
I think option
Only
is
one vertex is enough. If you take two
I think
vertices,
option A
like
is
either,
correct.
option is
yeah,
correct.
if you take the first one, if you check the first row, it's enough to check that.
Yes, sir.
Sir, 0 to 3.
Like if you want to find the SP4, so let's discuss in here itself. So here is, we check that here is 0.
4 0.
If you go
4
0 to, let's check
3.
here, 0 to 0, it's going to be infinite. 0 to 1, so 0 to 1 is 1 is there. 0 to 2 is what? 0 to 2 is 0 to 2 is going to be, here is infinite is given. Okay, 0 to 2.
Sir, we can check which is not common.
Yes, sir.
Yeah, that's the process which is not common. And
4
0
to
to
0.
4, if you see that 0 to 3, 0 to 3, 0 to, sorry, 0 to 2, no? So yeah, 0 to 2, there is no way to find. Is there any way to reach? There is 0, 1, is this, and this is the same matrix then. Here is going to be, that's why 4 is there, but here is infinite. So in each place it is infinite is written, okay? For 3 it is 3, and for 4 is there this way and then this way, which is 0. So if you go by this route,
First option.
0, so this is going to be 0, and here is 0 only. And now if other places is infinity is given, but we can reach to 4, right? We're using what? 0, 1, 2, 3.
Yes.
So 1 we are using, also 0 is also using.
Sir, we can check it in 2 steps. 0 to 3 and 4 to 0.
0 to 3, 0 to 3, yes, and 4 to 0, yes.
4 to 0.
4 to 0 if you want to reach, so by this way you can, yes. And yeah, this is there, these are the infinities. So this is the one, and then again the here is written the same. You can, it means you need to find the shortest distance from the vertices I to j using the vertices 0, 1, 2, 3. So that's why option A is going to be correct. Similarly for the other option, similarly for SP5. So I'm just leaving this question. This is exactly same, exactly Floyd-Warshel algorithm. I'm just keeping this question. I just need to go with the different problem, which is a MCST, the minimum cost spanning tree. So what is the minimum cost spanning tree? Spanning tree, we know, right? Spanning tree is just a subgraph or a graph, not subgraph, a part of graph, or exactly the graph, but which is a graph which span the whole graph. That is the spanning tree. And we want to find that spanning tree, which is, there can be many more spanning tree. Okay? There can be, for a graph, there can be many more spanning trees. There can be many more possible spanning trees there. But which spanning tree gives the minimum cost? That is the minimum cost spanning tree. So a spanning tree of an n-directed graph, this is a subgraph that is a tree which include all vertices of G. This is the definition of spanning tree, which is a subgraph, okay, and which include all vertices, and also a tree. That's the meaning here. Tree means what? Tree is a graph which not contain any cycle. That's the tree. How is the spanning tree different from a tree? Spanning tree is different from a tree. Spanning tree is the subgraph of G, and that subgraph should be a tree. Okay? It is a subgraph, and not only here is not the enough information is given. Here should be, it means that it should contain all vertices. If you are skipping the subgraph, means you can skip the
So
sum.
tree means the
vertices.
various branches containing all vertices.
So tree means, the simple definition of tree means it is a graph which does not contain any cycle. For the undirected graph we are seeing. Okay. Tree means it is a graph which does not contain any cycle. That's the tree. And a spanning tree means it is a subgraph which contain all vertices, and also a tree. So this definition is enough to find the spanning tree. And difference between the tree and the spanning, what is the difference between spanning tree and tree is, it is a subgraph. And what is the cost of a spanning tree? Just find the weight of it. And minimum cost is the minimum cost of the, there are many possible spanning tree could be possible, but which is going to be the minimum weight with the minimum weight. How to find? So there are two algorithms. One is Prim's algorithm, and another is Kruskal. Both we know. We just now have already discussed what is the Prism algorithm is. Prism algorithm is, suppose if you have graph, so you have to choose the minimum weight edge graph, and with respect to these vertices, again expand your vertices, expand your graph with those edges which have minimum. Just check with the, like, what are the edges which is connected with this vertex, no, and choose with that edge or go with that edge which have the minimum. So like this one, which is going to have the minimum. Okay, and now choose among these three vertex, what are the edges are connected, choose the minimum weight edge and expand according to that. Okay, like this you can expand, or this one or this one. So this is the Prim's algorithm, and Kruskal says choose the minimum weightages, like this one, this one, this one. Choose the minimum weightages. It will be in separate form. Finally, if you check one by one, if you do start checking, finally we'll get that, okay, like this, some graph will be formed. Okay, so by this way, this is the Kruskal algorithm. Means you have to choose the minimum weight edges, and if you finally you have
For Kruskal,
chosen
this
that,
minimum
yeah.
weight edges and Prim's is minimum vertex. Both are similar only, right? So what is the difference?
Sorry.
What is the difference between the algorithm of Prim's and Kruskal?
So that's why I'm saying, no, algorithm from Prim's is you have to choose the minimum. Like suppose you have this graph, no, like this one, you can see that. So if you if you see this graph, so Prim's says that choose the minimum weightage. So choose the first one, minimum weightage. So suppose you have chooses this one. Okay, this is the minimum. Now expand your graph with using these vertices. Okay, like which have the minimum using these two vertices, this one, right? Now using these three vertices which have the minimum. So if it is 7, this we know that suppose this is 7 here. So by this way. So using this, we are expanding with the whatever we have added previous one, we are expanding. Now from minimum this one. Now from minimum this one, like this. But the Prim's Kruskal is choose this one, okay, in the separated form, choose this one. Let me change the color. So Prim says choose this one, and then now which is now after choosing this one, which is minimum, this one. Now choosing this one, this is minimum. So see that now it is connected form. No? This is in the connected form. Now choose the minimum, this one. Now choose the minimum, this one. So now see that this is in the connected form. So these two are connected. Now choose minimum. So you will, if you choose that, this one. So this is going to be in the connected form if you see that. Okay. So these are the connected. Now choose minimum. This is going to be. So this is, see that now slowly you are choosing, and also slowly it is connecting. So this is the Kruskal. Now you are looking the difference between, right? This is Prism and this is Kruskal. Is it clear now?
Yes.
Yes, sir, clear.
This is the difference between the Prism and Kruskal. Kruskal is like this: choose the minimum weightage and add that. Choose the minimum add. But Prism is, suppose you have chooses the minimum one. Now from this, try to expand. So like this, and then now expand. Now, so you will choose like this. Slowly it is expanding. But Kruskal is choose the minimum kind of thing. Okay. So by these two algorithms, I hope it is clear. So let's solve the problem based on this one. I'm not going to explain now. This all whatever written is the same. Yes, the definition is the term is TV means. Here is TV means. TV means here. TV is the set of three vertices added to the MCST, and T is the set of three edges added to the MCST. So here TV means set of those vertices which in the minimum cost spanning tree, and TE is those edges which is in the minimum cost spanning tree. Using these two definitions, if you use that, there is a problem. Okay. This problem is, suppose this is the graph you have. Okay. The problem is, if you perform Prim's algorithm starting with the vertex R, then then the order in which the vertices will be added to the TV. T means here, if you do the minimum cost spanning tree, so what is going to be what is the order of the, if you start with from R, what is going to be the order if you do if you are doing Prim's algorithm. Please everyone solve this problem. This is going to be the last one problem. Okay. I'm just going to discuss the last one problem. The last, and also there is one problem which is the same as TV, but based on the Kruskal algorithm. That is, I will try to leave because after discussing, I think 10 will be reaches. It will be reaches to 10. So none of you have solved. All of you are getting this problem or not? Am I audible?
So actually, Prims and Kruskal are not sure of the algorithms. So I think only if it is explained in detail.
Just now I discussed. I don't know you were there or not. On this slide, I was discussing this on what is the Prim
Okay,
cell
so then I'll see the
Kruskal.
recorded session.
I don't know. You didn't get a very on this graph itself. I just discussed this on how what is the Prim cell Kruskal.
Yes, so you can solve.
So let's discuss the solution part. So draw the graph first. We have to draw the graph. Without that, we cannot. It will be very difficult. So the graph with respect to this adjacency matrix, the graph will be look like this. Now it says start from R. So let's think from the. So here is the initialized TV is equal to 5 means TV means what? TV is the tree with the vertex which is in MCT. We don't this is till now we don't have the vertices in the MCST, and the edges we don't have. We start with the vertex R. Okay, so we are doing from here is vertex R and edges till now. So which is going to be minimum now? Edge is what is the minimum edge we are doing from R now? So which is minimum is this URH. This is the next step. So this is RU. Sorry, UR is RU. So here is the next in the next step the vertex is going to, because in whatever if we started from this R, so this is going to which is going to be minimum, which is this edge and this edge it have, and we started from our edge we started from this vertex. So the minimum edge is going to be this as we have. So this is So edge is RU or RU or whatever the RU or you are going to write. So the next vertex is R, and then next is U, and the edge is going to be RU. Now once you have RU, now choose the which is minimum now in this, which is connected with the vertices U and R.
V.
Which vertex?
R.
V is there. Now, so the next step, if you see that V is there. This is the way. So this is now done, and this is the V is there. So if you see that TV means the vertices which will in the MCST. So these are the vertices, and edge will be what? VR or RV, whatever the VR RV edge is. And now from here, which is going to the minimum? So we want a tree, no? So we cannot the minimum with the U. So we have to go P, right? We have to go with the P. Yes. Amit have answered. Okay. Now in the next step is P is there. So if you say that P is there, the H is going to be this one.
So can't we choose?
Now in the next step,
So can't we choose UV?
so can you tell me why you cannot choose U? If you choose U, then what will happen? If you choose U, then what will happen? It will be a cycle. It will form a cycle. It will become a cycle. That's why we cannot choose. We are searching a tree, a spanning tree, not any graph. We are searching a tree. So tree doesn't contain any cycle. So that's why anyhow we have to go with the P. Now once you reaches P, so from P we have to start. So from P, now it is this part is done. Now this is which have minimum. So which 6 is the only connected with. So Q we have to perform Q, and then from Q, which is going to be minimum. So we have to choose with the P and Q, no? So which is minimum? S is going to be, either we can choose this one also, but it is 9 is greater than it. So we have to go with this one, 8. Now once you chooses 8, then now this is going to be this side. This is T, as here the T is there. So T is done. Now the TV, which is TV is actually the set of vertices which are in the MCST. So this is the order, and this is the vertices. Now the MCT is going to be this is the answer is asking. This is done. So this is the Kruskal will do. So this problem is that if you once you did this one, so the Kruskal is the same as, that is the easier part. So is that slide is okay, or whatever we discussed the question, is that clear, or I hope algorithm is also got clearer. So what is the algorithm? Please, if you have some minor doubt in the Kruskal and Prim's algorithm, just now I have discussed on this slide. One by one, how we will choose, or what is the Prims we have and Kruskal, and also Floyd-Warshel algorithm or Bellman, okay? And also Dijkstra algorithm. Okay? Is that clear now? Somewhat?
Yes.
I don't know. Okay. Only
Sir, this one, what you are
Answer
showing
is
is
there.
question number 1. Question number 1 you are showing, right, sir? That one, we need to find the X or what? That one.
Here is the find. We have to find the X value.
So if we have to find the X value, Prims will be better, right, sir? Not the.
Oh, so no,
Kruskal.
I know. So here is not for Prim. Say this is the for different problem. This is I just shown you. After assuming this is 7. This
Okay.
here is I was trying to explain you with this graph only. What is the difference between the Prims and the Kruskal? Okay. This problem is just I use this further to discuss Prims and Kruskal, not to solve.
Okay, sir. Actually, there are some questions where we need to find the X or X, so that the spanning tree will have X value, so that the spanning tree will have what value can be there for particular X, like that. There are some.
So same. You have to choose the minimum one. So it will surely give some value. it said it
Yeah,
should be,
so-
it is given that the spanning tree is some value, so that
Yeah.
which value we can choose, so that it will give that whatever the minimum value it says.
Okay, sir.
Either
So
if
in
you
that
go with
case,
the
we need
ans-
to
Yeah.
go with the prims, right, sir?
So in that case, I will suggest you go with the Kruskal is better than, because Kruskal is, choosing the minimum one, chooses the minimum one is there, right? After choosing the
Okay.
minimum, rest all from choose the minimum. So Kruskal will more help than the prims.
Okay, sir. Okay.
Okay, now I'm stopping the sharing here. So that's all for today. Okay, thank you so much for joining.
Thank you, sir.
And now we'll try to do the PYQ sessions will soon start. I think I thought maybe today is Wednesday, I have to give on Thursday itself. Now, okay, from Saturday we have session with the TA, So from Saturday we can give, okay. So we'll start the PYQ session soon, and then the vision session will be also scheduled soon from 27, I think so, or 25 or 25 or 27. Let's see. We'll get the soon update. Please check with by tomorrow evening, we'll get the update of the revision session also related to the PYQ sessions.
The revision sessions will be handled by you or TS?
So by me and Vishal is there, 2 person will handle with the revision.
Okay, sir. Thank you.
Sir,
Okay.
sir,
Yes.
excuse me.
Yes.
One more lot. What will the weightage for 1 to 4 week and 8 to this till 8 weeks, sir?
So 1 to 4, you can think that 1 to 4 is 15 to 20 marks, and 4 to 8 is again the 20. You can think 20, 20, 40, and then 60. Similar kind of.
Okay. Last week we'll be having the 40 marks, huh?
Last week means 8 to
last 4 weeks.
yeah 8 to 11 you can think, or 9 to 11 you can think more marks. So not exactly 60, it may be up and down, maybe 50 also. Some weightage will be on the calculus, may be given more, because calculus is more important once you do in the maths too.
Okay. 9 to 11.
But yeah, 1 to 4 you can think the weightages will be reduced in compare of others. So you can think it is of 20 or lesser than 20.
And between this graph theory and calculus, sir?
Yeah, between the graph will contain surely at least, see, in the graph you can think at least 15 or 20, and there is one maximum in my critical point is there. So you can assume that this is from 10 marks, so it reaches to 30 or 35. So anyhow it will be, reaches to, graph will contain 20, and then approx 35 and or 40, and one is a critical point will contain 20 marks, which reaches anyhow 55 or 60. Okay.
Thank you, sir.
How many questions will be there in the end term max?
Roughly you can assume, some questions have some part, so as it is of containing some 14 to 15 problem, but some questions have some parts, so that's why it reaches to 20. Some questions have some parts also. Some is the questions of problem have breakdown in some easy parts, so that you can do, or true false some problems you can get, that you can, if you know the concept, you can choose the correct option. So it may be reaches, if you include the sub parts also, it may reaches to 18 or 20. Otherwise, question wise, if you go with, then you can reaches to 14, 15.
Okay, sir. So will it be 1.5 hours exam?
1.5, no? This of 1.5 hour generally is that. No, 1 hour is for quizzes, so 1.5 is for intern. Yes.
Okay, sir. Thank you.
Okay. Thank you so much.
Thank you, sir.
Good night to all of you.
Thank you, sir.
Thank you.